There is a lie hidden in the most beautiful picture ever taken of our universe. You know the one. You have seen it on desktop wallpapers, in science textbooks, perhaps even printed on a t-shirt. It shows towering, majestic columns of rust-colored dust against a backdrop of piercing blue light. We call them the pillars of creation. They look like ancient stalagmites in a quiet cave, or perhaps the ruins of a celestial cathedral, silent, stoic, and eternal. They look like a place where you could float in peaceful suspension, watching the cosmos drift by. But this is an illusion. If you could actually stand there, floating near the tip of that leftmost pillar, you wouldn't find peace. You would be incinerated. These aren't stone monuments. They are eroding mountains of hydrogen gas, being blasted apart by the ultraviolet fury of newborn star. They are not standing still. They are evaporating. Every single year, a chunk of those pillars with the mass of 70 Earths is stripped away, lost to the void forever. The image you see isn't a landscape. It is a snapshot of a massacre. This is the deception of the nebula. We look at these cosmic clouds, the Orion Nebula, the Carina Nebula, the Crab Nebula, and we see art. We see brushstrokes of pink and gold, frozen on a canvas of black velvet. But the only reason they look peaceful to you is that you are seeing them from light years away, and you are seeing them frozen in time. In reality, a nebula is a hurricane. It is a chaotic storm of shock waves, screaming radiation, and magnetic turbulence. It is a place where gravity crushes gas until it ignites, and where dying stars detonate with enough force to rip solar systems apart. Welcome to the truth behind the canvas. Over the next hour, we are going to tear down the static image and hit play on the most violent movie in the universe. We are going to trace the invisible lines that connect these terrifying clouds directly to the blood in your veins and the gold in your jewelry. But before we can understand how these clouds forged you, we have to understand what they actually are. Because I guarantee they are not what you think. Let's start with a paradox that breaks the human mind. When you look at the Orion Nebula, you see a thick, glowing fog. Science fiction movies have trained us to believe that if a spaceship flew into a nebula, the pilot wouldn't be able to see past the windshield, like driving through a heavy storm in Seattle. You imagine swirling mists and thick clouds that you could almost scoop up with a bucket. Here is the reality. The densest part of a nebula is a cleaner vacuum than the best vacuum we can create in a laboratory on Earth. Think about the air you are breathing right now. In a single cubic centimeter of the air in your rooms, a space the size of a sugar cube, there are roughly 10 billion gas molecules. That is a 1 followed by 19 zeros. It's crowded. Now, let's transport that sugar cube to a nebula. In a dense stellar nursery, that same cubic centimeter holds maybe 10,000 particles. That's it. To a physicist, that is a vacuum. If you were essentially anywhere else in the universe, we would call that empty space. And yet, because nebulae are so incomprehensibly vast, stretching across dozens or hundreds of light years, those sparse particles add up. When you look through 10 light years of that nothingness, it becomes an opaque wall of glowing color. It is a ghost. It is an object that only exists because of the scale from which you view it. If you were inside it, the nebula would vanish. You would look around and see only black space with slightly brighter stars. You are trapped in a paradox. The structure exists only when you are far enough away to be irrelevant. So, if these clouds are just ghosts, mere whispers of gas, why are they so dangerous? Why do I call them violent? Because even a ghost can scream if you hit it hard enough. To understand the violence, we have to look at the history of how we found these things. It's funny to think that for most of human history, nebulae were considered trash. In 1764, a French astronomer named Charles Messier was obsessed with hunting comets. Comets were the prize. They were dynamic. They moved. They were exciting. But Messier kept getting distracted by these annoying, fuzzy, stationary patches in the sky that looked like comets but refused to move. He hated them. They were nuisances. So, he made a list of them. He created a catalog of objects to ignore so that other comet hunters wouldn't waste their time. He marked the Crab Nebula as M1, the first mistake. He marked the Orion Nebula as M42, the most famous list of deep sky objects in history. The Messier catalog began as a list of garbage. He saw them as static smudges on the lens of his telescope. It took another 100 years for a man named William Huggins to realize what they really were. In 1864, Huggins pointed a spectroscope at the Cat's Eye Nebula. He expected to see the spectrum of stars, a rainbow broken by dark lines. Instead, he saw a single bright green emission line. He realized instantly that he wasn't looking at a cluster of distant suns. He was looking at a cloud of luminous gas. But gas doesn't just glow on its own. It needs energy. It needs a trigger. And this brings us back to the violence. Deep inside these clouds, hidden behind veils of dust that standard telescopes can't penetrate, baby stars are throwing tantrums. We call them protostars. When a star is born, it doesn't just switch on like a light bulb. It fights for its life. As gravity pulls gas inward to feed the growing star, the magnetic fields get twisted into tight coils. These coils launch jets of superheated matter out of the star's poles like a cosmic railgun. We call these Herbig-Haro objects. Imagine a jet of ionized gas screaming through the silence of space at 700,000 kilometers per hour. That is nearly 2 million miles per hour. When that supersonic jet slams into the surrounding slow-moving gas of the nebula, it creates a shockwave of epic proportions. The gas is instantly heated to 10,000 degrees Kelvin. It glows like a neon sign in the desert night. This is what you are missing in the photograph. You see a pretty pink swirl. The universe feels a sonic boom. In fact, if we could translate the data from these nebulae into sound, a process called sonification, the Orion Nebula wouldn't sound like a choir of angels. It would sound like a cacophony. The inner regions generate low-frequency hums from the radiation pressure of massive stars, overlaid with the high-pitched screeches of these shockwaves ripping through the dust. It is a construction site. It is a war zone where gravity is trying to build order and radiation is trying to blow it all apart. And the stakes of this war are existential. Let's go back to the pillars of creation. The reason that image from 1995 and the newer one from the James Webb Space Telescope in 2022 hits us so hard is that it looks permanent. But the comparison between those two images and the data we have gathered in the years between them reveals a terrifying truth. The pillars are dying. There is a cluster of massive, hot blue stars just off camera, above the pillars. These are O-type stars, the bullies of the stellar neighborhood. They are blasting out ultraviolet radiation, so intense that it is literally boiling the pillars away. This process is called photoevaporation. The gas is being heated and stripped off the surface of the pillars, streaming away into space. Here is the drama that the static image hides. Inside those pillars, there are dense knots of gas trying to collapse into new stars. They are hiding behind the walls of the pillar, sheltered from the UV glare. It is a race against time. Can gravity pull the knot together tight enough to ignite a star before the protective cloud is blown away by the bullies outside? If the pillar evaporates too fast, the baby star is cut off from its fuel supply. It is born stunted, a brown dwarf that will never shine, or it is simply ripped apart before it can even form. The pillars of creation are also the pillars of destruction. It is a nursery, yes, but it is a nursery built on the edge of a volcano. This duality, creation and destruction, beauty and violence, is the heartbeat of the cosmos. And it is not just happening out there. It is the story of you. This is the part where the science becomes personal. I want you to look at your hand. Look at the skin, the veins, the ring on your finger. Every atom of carbon in your cells, the oxygen in your lungs, the iron in your blood, the gold in that ring, none of it existed when the universe began. The Big Bang produced only hydrogen, helium, and a tiny dash of lithium. A boring, sterile universe. So, where did the rest come from? It came from the nebulae. It came from the furnaces. The calcium in your bones was forged in the crushing heat of a dying star. The gold in your jewelry was likely created in the violent collision of two neutron stars, a kilonova, which blasted a Jupiter-sized mass of pure gold into the void. But here is the crucial link. Those heavy elements didn't just teleport into your body. When those stars died, they exploded. They became nebulae. They became the cosmic graveyards. These expanding clouds of debris, rich in iron and silicon and gold, drifted through the galaxy for millions of years. Eventually, they hit a stellar nursery. The death of the old stars seeded the birth of the new. A shockwave from a supernova might have slammed into a quiet cloud of gas, triggering it to collapse, starting the cycle all over again. Our own solar system, the sun, the earth, you, was born in one of these clouds. We are the result of a nebula that collapsed 4.5 billion years ago. We are the afterlife of stars that died long before the earth existed. So, when we look at the deceptive canvas of a nebula, we are not looking at an alien landscape. We are looking at our own history. We are looking at the factory floor where we were built. But the factory is not safe. It is a place of extreme hazards. Consider the temperature extremes. In the core of a collapsing star within a nebula, the temperature can spike to 100 billion Kelvin in the final moments before a supernova. Yet, the molecular cloud surrounding it, the raw material for the next generation, hovers at 10 Kelvin. That is minus 263 degrees Celsius. It is just a hair's breadth above absolute zero. In this environment, you have the hottest fires in the universe burning next to the coldest ice. It is a thermodynamic nightmare. And it is within this nightmare that the most delicate chemistry of life begins. We used to think that space was too hostile for complex chemistry. We thought amino acids, the building blocks of life, could only form in warm, wet ponds on planets like Earth. We were wrong. Radio telescopes have detected glycine and other complex organic molecules floating in these deep freeze clouds. The ingredients for life are not rare. They are cooking right now in the Orion Nebula, protected by the very dust that Messier found so annoying. The nebula is not just a star factory. It is a chemistry lab. It is mixing the chemicals that might one day become the eyes and hands of a creature looking back at the sky, wondering where it came from. But we are getting ahead of ourselves. To understand how the dust becomes a living thing, we first have to understand the machines that do the work. We have to talk about the stars themselves. We often think of stars as eternal. The sun has been there every day of your life. It will be there every day after you are gone. But on cosmic timescales, stars are fragile. They live on a knife-edge balance between two opposing forces, gravity trying to crush them in, and nuclear fusion, trying to blow them apart. For millions of years, this battle is a stalemate. The star shines, it is stable, but eventually the fuel runs out. The balance breaks, and when gravity wins, it doesn't win gracefully. The most terrifying event in the universe is the death of a massive star. It is the engine that drives the cycles of the nebula. It is the violence that creates the beauty, and it all hinges on a single element, a killer lurking in the periodic table: iron. We are going to take a journey now, deep into the heart of a dying giant. We are going to watch the clock tick down, the final 24 hours of a star that has lived for 7 million years. We are going to witness the iron catastrophe, the moment where physics betrays the star and gravity collapses a core the size of Earth into a city-sized sphere in less than a single second. This is the moment the canvas rips. This is the moment the static image begins to move. You see, the nebula isn't just a place, it is a time. It is the brief, chaotic intermission between the death of one star and the birth of another. It is the recycling center of the galaxy, and nothing, absolutely nothing, is wasted. The story we are about to tell is the story of that recycling. It is a story of how the universe breaks things to make them better. It is a story of how destruction is just creations in disguise. So, forget the peaceful wallpapers. Forget the silent, floating clouds. Strap in. We are diving into the storm. We are going to watch a star eat its neighbors to stay young. We are going to see the gold rush of a neutron-star collision. We are going to watch the pillars crumble. The canvas is deceptive, but the reality is far more beautiful and far more terrifying than any painting could ever be. Let's begin with the birth. Let's go to the dark places where the night sky has a hole in it and watch what happens when gravity decides to wake up. When we talk about the dark places, we are talking about the cold. It is a cold so profound that it stops atoms in their tracks. We are drifting now into a molecular cloud. To your eyes, if you were floating here, this would look like a hole in the universe, a patch of nothingness where the stars have simply vanished. But this is not emptiness. This is potential. This is the waiting room of creation. There is a misconception about these clouds that we need to clear up right now. When you see sci-fi movies, nebulae are often depicted like thick pea soup fog, clouds you could hide a spaceship in, swirling around the wings of your craft. But the reality is far stranger. These clouds, even the densest ones, are a more perfect vacuum than any we can create in our best laboratories on Earth. If you were to cup your hands and scoop up a section of this thick cloud, the size of the entire Earth, it would weigh only a few kilograms. It is a ghost of a cloud, a whisper of gas spread over light years. And yet, because it is so vast, because it stretches across distances your mind struggles to comprehend, it has mass, immense, crushing mass. And where there is mass, there is gravity. For millions of years, this cloud hangs in the dark, balanced in a delicate standoff. The internal pressure of the gas wants to expand, to drift apart into the void. But gravity wants to pull it all inward. It is a stalemate, a cosmic pause. Then, something happens. Maybe a shockwave from a dying star nearby ripples through the dark. Maybe the cloud drifts through a dense spiral arm of the galaxy. The balance tips. Gravity wins. The collapse begins. It is not a gentle process. It is a free fall. The gas begins to rush inward, spinning, heating up, falling toward a center that is getting denser and hotter by the second. But we aren't going to look at the center just yet. We are going to pull back. We are going to zoom out to see the architecture of this nursery, because this is where the story of our origins becomes a story of violence. You have seen the image. Everyone has. It is perhaps the most famous photograph ever taken by the human species. The pillars of creation. 3 towering fingers of gas and dust, standing against a backdrop of glowing blue light. When the Hubble Space Telescope first captured this, in 1995, it changed the way our species looked at the universe. It gave space a geography. It turned the void into a landscape. These pillars look like ancient stalagmites rising from a cave floor, or majestic mountains standing firm against the sky. They look like statues, permanent, serene, and eternal. But this is a lie. If you could speed up time, if you could watch these pillars with the eyes of the universe, you wouldn't see a statue. You would see a catastrophe. We are looking at an erosion event. These pillars are not growing. They are being destroyed. They are being blasted apart, minute by minute, by a force so powerful it defies imagination. To understand what is happening here, you have to understand the bully in the playground. Just off camera, sitting above those pillars, is a cluster of massive newborn stars. These are O-type stars, monsters that burn hot and blue, thousands of times brighter than our sun. They are young, violent, and they are screaming radiation into the void. They are unleashing a torrent of ultraviolet light, a stellar wind that slams into the dense gas of the pillars. This is where the sandcastle metaphor becomes terrifyingly real. Imagine you are a child on the beach. You have built a magnificent castle. It has towers, walls, a keep. But the tide is coming in. And this isn't a gentle tide. It is a tsunami. You are frantically trying to pack the sand tight, trying to hold the structure together. But the water is stripping the walls away, layer by layer. That is what is happening to the pillars of creation. They are evaporating mountains. The scientific term is photoevaporation. The intense light from those massive stars is boiling the outer layers of the pillars, stripping away gas and dust, launching it into space. The smoke you see rising from the tops of the pillars in those famous images, that is the material of future solar systems being vaporized and blown away forever. We now have images from the James Webb Space Telescope that peel back the dust. In the near-infrared, the pillars look different, ghostly, translucent, glowing with a rusty red hue. And through this new lens, we can see the tragedy of the nursery. We can see that the pillars are shrinking. They are losing mass at a rate of roughly 70 Earths every single year. Think about that. Every year, 70 planets worth of potential life, 70 worlds of rock and water and possibility are simply erased, blown out into the void as useless dust. This creates a dramatic, high-stakes race against time for the stars forming inside. Deep within those pillars, hidden in the densest knots of gas, gravity is trying to build new stars. These are the protostars. They are the children hiding in the sandcastle. They need to gather enough mass to ignite, to turn on their nuclear engines, and become self-sustaining stars. But the shelter they are hiding in is disappearing. If the pillar evaporates before the star is finished forming, the star is cut off. It is born premature. It will never gather enough mass to shine brightly. It will be a brown dwarf, a failed star, cold and dark, drifting forever. It is a race between gravity pulling material in and radiation blasting material away. And the margins are razor thin. This is the chaotic reality of the stellar nursery. It is not a place of peace. It is a war zone of radiation and shock waves. The beauty we see in the telescope, the reds, the golds, the deep blacks, is the beauty of destruction. It is the visual signature of a structure falling apart. But let's pause here for a moment. I want you to do something with me. I want you to close your eyes for a second. Picture the pillars of creation. In your mind, you know the shape, those three fingers reaching up. Now ask yourself, why do you find it beautiful? Is it because it looks timeless? Is it because it looks like a monument? Now open your eyes. I want you to challenge that assumption. What if I told you that in the time it took you to picture that image, the structure has changed? What if I told you that the light we see from the pillars left them 7,000 years ago, and astronomers believe a supernova shockwave may have already toppled them? We might be admiring a ghost. We are looking at a ruin and calling it a cathedral. How does that change the way you feel about the eternal cosmos? Does the fact that it's temporary make it less beautiful, or does it make it more precious? Let me know what you think in the comments. Are we looking at art, or are we looking at a graveyard in the making? Now, let's go back inside. Let's go deeper, past the eroding walls of the pillars, into the dark knots where the stars are actually being born. If the outside is a war zone, the inside is a factory floor where the machinery has gone haywire. We used to think that stars turned on quietly. We imagined that gravity pulled the gas in. The ball got tighter and tighter, and eventually, click, the lights went on, and a star was born. A gentle sunrise in the dark. We were wrong. Star birth is a violent, screaming tantrum. When a protostar forms, it is spinning. The gas falling into it forms a disk, an accretion disk, spiraling down like water into a drain. As the star feeds, it gets hot. Magnetic fields begin to twist and tangle around the newborn core. The pressure builds until the star can't take it anymore. And then, it fires. It doesn't just shine, it erupts. The protostar launches twin jets of superheated, ionized gas from its poles. These aren't gentle streams. These are supersonic cannons. The material in these jets is traveling at speeds of over 700,000 kilometers per hour. That is nearly 500,000 miles per hour. Imagine a newborn baby, but instead of crying, it screams shockwaves that tear through the nursery. These jets blast out into the surrounding nebula, slamming into the cold, slow-moving gas that hasn't fallen into the star yet. When a 700 km/h jet hits a stationary cloud of cold gas, the result is a massive sonic boom. The friction is so intense that the gas is instantly heated to thousands of degrees. It glows. It lights up the dark like a neon sign. Astronomers call these Herbig-Haro objects. In the images from Hubble and Webb, they look like beautiful glowing streaks, smears of bright green, hydrogen red, and sulfur yellow. They look like laser beams cutting through the smoke. But physically, they are colossal shock fronts. They are the evidence that this star is fighting for its space. It is clearing a cavity around itself, pushing back the cloud that made it. This is the aha moment of star formation. The star doesn't just passively accept its environment, it actively shapes it. It fights back. These jets can stretch for light years. Think about that scale. A single newborn star, effectively a microscopic dot in the galaxy, creates a structure that is trillions of miles long. It is announcing its arrival to the universe with a shout that echoes across the dark. And this process is messy. It is chaotic. The jets aren't always straight. They wobble and twist as the star spins. They pulse. We can see knots in the jets, bullets of gas fired out at different times, recording the history of the star's feeding frenzies. It's like reading the rings of a tree, but instead of wood, we are reading explosions in the sky. This is the environment your atoms came from. Every particle of carbon, oxygen, and nitrogen in your body right now has been through this. Before it was part of you, before it was part of the earth, it was dust in one of these violent clouds. It was blasted by the UV radiation of a dying sister star. It was caught in the accretion disk of the sun It was ejected in a Herbig Hero jet, thrown out into the cold, and then pulled back in again. You aren't made of static matter. You are made of recycled chaos. We look at the Orion Nebula or the Eagle Nebula and we see peace, but the data tells us otherwise. We hear the sound of these places when we translate the electromagnetic waves into audio, a technique called sonification. The center of the Orion Nebula doesn't sound like a choir of angels. It sounds like a roar. It sounds like the wind of a hurricane. It is a cacophony of radiation pressure and magnetic screaming. This is the eroding nursery. It is a place where creation and destruction are the exact same thing. The very forces that trigger the collapse of the cloud, the shock waves, the radiation, are the same forces that try to destroy the stars once they are born. It is a balance on a knife's edge. And for the stars that survive, for the ones that win the race against the eroding pillars that manage to hold on to their mass and ignite their fusion cores, their journey is just beginning. They have survived the storm of their birth. They have cleared their little pocket of space. The jets fade. The disk settles down into planets. The star enters the long, stable burn of its main sequence life. It seems like the violence is over. It seems like the star has won. But deep in the core, a new clock has started ticking. A countdown has begun. Because the star is now burning its fuel, it is consuming itself to stay alive. And one day the fuel will run out. The gravity that started this whole story, it hasn't gone away. It is still there, waiting. It is patient. It let the star have its moment in the light, but it will eventually come to collect. We have seen the nursery. We have seen the cradle being rocked by supersonic winds. Now, we must look at the life that follows. But more importantly, we must look at the death. Because if you think the birth was violent, if you think the erosion of the pillars was terrifying, you're not ready for what happens when the engine stops. The nursery is gone. The sandcastle has washed away. The star is alone in the dark, and the iron is coming. You are floating in the aftermath of a creation story that has turned terribly quiet. The nursery we just left, that chaotic, wind-swept cathedral of gas, where the star was born, is gone. The violent tantrums of the Herbig Hero jets have faded into the deep silence of space. The star has matured. It has entered the long, stable years of its life, drifting through the galaxy like a lantern in a dark room. When you look at the images taken by our most powerful telescopes, by Hubble or the James Webb, you see these regions of space as paintings. They are frozen in time, majestic and still. We hang them on our walls. We use them as screensavers. We project our own desire for peace onto these cosmic clouds, imagining them as serene celestial gardens where nothing ever goes wrong. But this stillness is a lie. It is a trick of scale and a deception of time. If you could speed up the clock, if you could press fast forward on the cosmos, you would see that these nebulae are not paintings at all. They are battlegrounds. They are shark tanks. And the peace you see is merely the tension before the snap. History has always struggled to understand these ghostly shapes. In 1764, the comet hunter Charles Messier created his famous catalog of deep sky objects, listing things like the Crab Nebula and the Orion Nebula. But he didn't list them because he found them beautiful. He listed them because they were nuisances. To him, they were just frustrating fuzzy patches that looked like comets, but refused to move, distractions that needed to be ignored, so he could do real science. It wasn't until William Huggins pointed a spectroscope at the Cat's Eye Nebula in 1864 that we realized these weren't just clusters of stars, but vast clouds of glowing gas. Yet even then, we couldn't comprehend the violence hidden within the mist. We have this persistent idea that a nebula is a thick cloud, like a London fog or a thunderhead on Earth. Science fiction shows ships hiding in them, submerged in a soup of dense gas. But the reality is far stranger. These clouds are ghosts. The density of a typical nebula is a paradox that breaks the human mind. On Earth, the air you are breathing right now contains roughly 10 billion particles in every cubic centimeter. In a nebula, you might find 10,000 particles in that same space. That is not a cloud. That is a vacuum better than any we can create in our finest laboratories on Earth. If you were to scoop out a chunk of a nebula the size of our entire planet, it would weigh only a few kilograms. So how can something so empty be so dangerous? Because gravity does not care about emptiness. It only cares about mass. And when you sum up those tenuous particles over light years of distance, you get monsters. In the densest clusters of these clouds, the stars are not drifting in isolation. They are packed together in a chaotic dance, swarming like bees in a hive. And just like in any overcrowded ecosystem, resources become scarce. Space is not big enough for everyone. This is where we meet the vampires. Astronomers call them blue stragglers, a name that sounds almost clumsy, but the reality of their existence is pure cosmic horror. According to the laws of physics, massive stars burn bright and die young. They should turn red and fade away quickly. But when we look into the hearts of ancient clusters, we see these stars, hot, blue, and massive, that simply shouldn't be there. They are too young for their environment. They are anachronisms. For years they were a mystery, until we realized what they were doing. These stars are not young. They are thieves. They are born in binary systems, paired with a companion star. As they age, instead of accepting their death, they begin to feed. They strip the outer layers of gas off their partner, siphoning mass through a gravitational straw. They consume the flesh of their neighbor to refuel their own tanks. The victim star is left as a withered husk, a stripped core, while the predator star shines with a stolen blue youth. It is a cannibalistic ritual played out over millions of years, a desperate attempt to cheat the inevitable dark. This brings us to a difficult realization about the universe we inhabit. We look at the night sky and see beauty, but the mechanics driving that beauty are often built on destruction. The blue straggler survives only by destroying its companion. It stays bright only by making another go dark. I want you to pause for a moment and think about that. We often project human morality onto the cosmos, looking for good or evil in the dark. But out here, there is only survival. If you were a star, trapped in the freezing void, running out of fuel, and you had the chance to steal a few billion years of life from the star next to you, would you do it? Does the drive to exist justify the consumption of another? It is a question that makes us uncomfortable because it reminds us that nature is not kind. It is merely efficient. I'd love to hear your take on this cosmic ethics problem. Drop a comment below. Are these vampire stars monsters, or are they just survivors doing what physics demands? While the blue stragglers fight their external battles, a much more terrifying enemy is waking up inside the heart of our solitary massive star. We have left the cluster now. We are back with the single massive giant we watched form in the last chapter. It has survived the nursery. It has avoided the vampires, but it cannot avoid itself. The star is fighting a war against its own gravity. For millions of years, it has held the darkness back by fusing hydrogen into helium. This fusion creates the outward pressure that acts as a pillar, holding up the unimaginable weight of the star's outer layers. But the hydrogen eventually runs out. The pillar cracks. Gravity pushes in. The core heats up, and the star gets desperate. It starts fusing helium into carbon, then carbon into neon, then neon into oxygen. This is the onion skin model of a dying star, concentric layers of heavier and heavier elements being forged in the crushing heat of the core. But with each new fuel source, the star gets less energy out of the deal. It has to burn faster and hotter just to stay in the same place. It is burning through its inheritance at a suicidal rate. The hydrogen burning phase lasted 7 million years. The helium burning phase lasted 500,000 years. But as we get to the end, the timeline collapses. The carbon burns in 600 years. The neon burns in 1 year. The oxygen burns in 6 months. The star is screaming through its life, frantically changing fuels to keep the crushing weight of gravity at bay. And then, it hits the wall. Silicon. The day the star starts burning silicon is the last day of its life. This is not a metaphor. The final phase of a massive star's life, the silicon burning phase, lasts roughly 24 hours. Imagine that. A structure that has existed for millions of years. A sun that has perhaps warmed planets and witnessed the rise and fall of civilizations. Now, has a life expectancy of 1 single day. Deep in the core, the temperature hits 3 billion degrees. The silicon atoms are being smashed together to form something new. They are forging ash. They are forging the one element that signals the end of the universe's ability to generate energy through fusion. They are forging iron. This is the iron catastrophe. Iron is the most tightly bound nucleus in the cosmos. It is a dead end. Fusing iron doesn't release energy, it consumes it. Up until this moment, every fusion reaction in the star's core has produced a net surplus of energy, a little pushback against gravity. But fusing iron costs energy. It is a heat sink. The moment iron is formed, the fire goes out. The engine stops. The pillar that has held up the weight of the star for eons simply vanishes. What happens next is the most violent event in the universe since the Big Bang. Gravity, which has been waiting patiently for millions of years, wins instantly. In less than a second, literally within a fraction of a heartbeat, the iron core, which is about the size of the Earth, collapses into a ball the size of a city. It shrinks from 8,000 miles across to 12 miles across in milliseconds. The particles are packed so tightly that electrons are smashed into protons, turning the entire core into a solid ball of neutrons. This is a density that defies language. A teaspoon of this neutron material weighs 1 billion tons. The outer layers of the star, the vast gaseous envelope that makes up the rest of its bulk, suddenly have nothing to stand on. They rush inward at 25%, the speed of light. They are falling into the hole where the core used to be. They slam into the ultra-hard neutron core and bounce. The rebound creates a shockwave of unimaginable power. This shockwave stalls for a moment, fighting against the infalling matter, until it is revitalized by a flood of neutrinos, ghostly particles generated in the core collapse. The shockwave rips outward, tearing the star apart. This is the supernova. It is an explosion so bright that for a few weeks, this single star will outshine the entire galaxy of hundreds of billions of stars combined. It releases more energy in 10 seconds than our sun will release in its entire 10 billion year lifetime. It is a flashbulb popping in the dark cathedral of the cosmos, announcing the death of a giant. But it is not just a death. As the star rips itself apart, it blasts its guts out into the void. All those elements it spent its life forging, the carbon, the neon, the oxygen, the silicon, are thrown violently back into the nebula from which it came. And this is where the story circles back. We started this journey looking at nebulae as nurseries, as the places where stars are born. But now, looking at the expanding debris field of this explosion, we see the nebula for what it truly is, a graveyard. The beautiful, colorful wisps of the Veil Nebula, or the Crab Nebula, are not clouds of potential. They are the shredded remains of a corpse. They are the expanding shrapnel of a stellar suicide. The atoms in these clouds are superheated, traveling at millions of miles per hour, glowing with the energy of the explosion. Yet, there is a profound beauty in this violence. If the star had not died, if it had not collapsed and exploded, the iron would have stayed locked in the core forever. The carbon would never have drifted out to become the backbone of organic chemistry. The oxygen would never have filled the lungs of a future creature. The iron catastrophe is a disaster for the star, but it is the necessary sacrifice for everything else. The nebula is a place of paradox. It is a vacuum that looks like a cloud. It is a nursery that is also a tomb. It is a silent painting that is actually a roaring explosion. The star is gone now. A city-sized sphere of neutrons is spinning in the dark where the giant once stood, a pulsar beaming radiation like a lighthouse across the galaxy. The shock wave is expanding, sweeping up the dust and gas of the interstellar medium, pushing it into new clumps, new knots, new seeds. The dust is settling, the violence is cooling, and in the darkness of this cosmic graveyard, something is beginning to clump together again. The death of the father has provided the substance for the son. The iron is cooling. The gold, forged in the heat of the collapse, is drifting through the void, waiting to be caught by a new gravity well. We have seen the birth. We have seen the life. We have seen the violent, sudden death. But the story of matter is not over, because that gold, that iron, that carbon, it has to go somewhere. It doesn't just float forever. It finds a new home. And sometimes that home is a small, rocky world, orbiting a yellow dwarf star. The predator has eaten its fill. The gravity has taken its toll. But the treasure has been released. The nursery is open for business once again. And this time, the ingredients are richer. The universe is recycling itself, and the next chapter is about to begin. The dust is calling. To understand the true cost of that dust, the dust that now settles so quietly in the cosmic graveyard, we must rewind the tape. We must go back to a time before the silence, before the cooling, before the recycling began. We have to go back to the moment the father died. Imagine you are floating in the deep vacuum, a safe distance from a monster. This is not a polite yellow star like our sun, which burns with a steady billions-year patience. This is a high-mass star, a titan weighing 25 times the mass of the sun. It is a blazing blue-white giant, screaming its energy into the void, living fast and destined to die young. For millions of years, this star has been a battlefield. A war has been raging in its deep interior, a stalemate between two cosmic titans, gravity and fusion. Gravity is the patient, crushing force that wants to pull every atom of the star inward, collapsing it into a microscopic point. It is relentless. It never sleeps. It never tires. Pushing back against this crushing weight is fusion. The explosive energy generated in the core, the heat of atoms smashing together to create light and pressure. For 7 million years, the war has been a draw. Gravity pushes in. Fusion pushes out. The star shines. It is stable. It is alive. But this stability is an illusion. It is a ticking clock, disguised as a diamond in the sky. Deep inside, the star is running out of fuel. It has spent its life burning hydrogen into helium, the standard currency of the cosmos. But massive stars are voracious. They burn through their hydrogen. not in billions of years, but in mere millions. When the hydrogen runs out, the star doesn't just fade away. It panics. Gravity senses weakness and squeezes the core tighter. The temperature spikes. The star begins to burn helium into carbon. This buys it some time, about 500,000 years. But the ash of one fire becomes the fuel for the next. The cycle accelerates. It becomes a frantic race against the crushing dark. Helium turns to carbon. Carbon fuses into neon. Neon burns into oxygen. Oxygen fuses into silicon. With each step down the periodic table, the star gets hotter, denser, and more desperate. The timelines shrink from millions of years to thousands, then to centuries. By the time the star is burning oxygen, it has only a year left to live. It has become a chaotic onion of burning shells, a terrifying factory of elements, shuddering under its own weight. And then, we arrive at the final day. The star has entered the silicon burning phase. This is the terminal countdown. The core temperature has reached a staggering 3 billion degrees. At these temperatures, the physics of the everyday world break down. Photons are so energetic, they can shatter atomic nuclei. The star is no longer just a fusion reactor. It is a frantic engine of transmutation, desperately smashing silicon atoms together to hold back the crushing hand of gravity. This phase does not last for millions of years. It does not last for centuries. It lasts for exactly one day, 24 hours. Imagine the sheer scale of that consumption. A star that has lived for eons is now burning through its remaining life force in the time it takes the Earth to rotate once. It is a dying beast, thrashing against the inevitable. If you were watching from the outside, you might see the surface shudder, vast winds of gas being blown off into space, but you would have no idea that the heart of the monster has less time remaining than a standard iPhone battery. The core is frantic. It is fusing silicon into sulfur, into argon, into calcium, into titanium, chromium, and manganese. It is climbing the ladder of the elements, forging the heavy metals that will one day build the skyscrapers and the bridges of a civilization that does not yet exist. But it is doing so at a cost that it cannot afford. This brings us to a pause in the chaos, a moment to reflect on what we are actually seeing. We often look at the night sky and see it as a symbol of eternity. Fixed stars, the ancients called them. We take comfort in their permanence. We build our calendars, our mythologies, and our navigation systems around the assumption that the stars are always there, unchanging and reliable. But if you look closely at the physics, you realize that the universe is not a static painting. It is a dynamic, violent, and precarious balancing act. Every light you see in the sky is a bomb that is currently exploding, held together only by its own gravity. I want you to take a second and think about that fragility. We live our lives assuming the ground beneath our feet and the sun above our heads are guarantees. But in the grand scheme of the cosmos, stability is the exception, not the rule. The universe is defined by these moments of sudden, catastrophic change. So, here is a question for you to ponder, and I'd love to read your thoughts in the comments below. If you knew that the stability of your world was just a temporary stalemate between opposing forces, like the gravity and fusion in a star, would it change how you live your main sequence, your day-to-day life? Do we, like the stars, need a deadline to shine our brightest? Pause the video if you need a moment, leave a comment, and let's get back to the countdown, because the clock is hitting 0. The 24 hours are up. The silicon is gone. In the center of the star, the fusion process creates a new element. Ash piles up in the core. It is element number 26 on the periodic table. Iron. This is the iron catastrophe. Iron is the poison pill. It is the cosmic grim reaper. Throughout the star's life, every fusion reaction has been exothermic, meaning it released more energy than it took to start. Hydrogen to helium releases energy. Helium to carbon releases energy. This energy provides the outward pressure that holds up the star against gravity. It is the rent payment that keeps the landlord at bay. But iron is different. Iron is the most tightly bound nucleus in the universe. It is an energetic dead end. To fuse iron into anything heavier requires you to add energy, not release it. Fusing iron doesn't produce heat. It consumes it. The moment the core turns to iron, the fusion reactor shuts down. The fire goes out. The outward pressure that has held up the star for 7 million years vanishes instantly. It is not a slow fade. It is a sudden, terrifying silence in the engine room. Gravity, which has been waiting patiently since the dawn of the star, suddenly finds the door unlocked. There is nothing left to hold it back. What happens next is the most violent event in the universe since the Big Bang. In the fraction of a second, less time than it takes for your heart to beat, less time than it takes for a synapse to fire in your brain, the iron core collapses. We are talking about an object roughly the size of the Earth. Imagine the Earth, the mountains, the oceans, the cities, the vast plains. Now, imagine crushing the entire Earth into a sphere the size of a city. Manhattan, London, Tokyo. That is what happens to the core of the star. It collapses from 8,000 miles across to barely 12 miles across. It happens at a speed of nearly 45,000 miles per second, about a quarter of the speed of light. The outer layers of the star, suddenly unsupported, rush inward to fill the void. This is not a gentle settling. It is a freefall of unimaginable proportions. The equivalent of 1 million Earths crashing inward at relativistic speeds. As the core collapses, the temperature skyrockets to over 100 billion degrees. The iron atoms are smashed so close together that they dissolve. Electrons are forced into protons, merging to become neutrons. The core transforms into a singular, ultra-dense ball of neutronium. It is a city-sized atomic nucleus. And then it stops. The collapse hits a wall. The neutrons are packed so tightly that the laws of quantum mechanics intervene. They cannot be squeezed any further. The strong nuclear force, the strongest force in nature, snaps into action. The core, collapsing at 25% the speed of light, slams into this neutron wall and comes to a dead halt in a millisecond. But the rest of the star is still falling inward. The outer layers of the star crash onto this super-hard neutron core. Imagine dropping a rubber ball onto a concrete floor, but magnify the energy by a factor of 1 trillion trillion. The infalling gas hits the core and bounces. This is the hard bounce. The energy of that impact is transferred into a shockwave of unimaginable power. It turns the implosion inside out. A wave of kinetic energy and incomprehensible heat begins to race outward, tearing back through the infalling layers of the star. This is the moment of death, and it is the moment of birth. The shockwave rips through the star, blasting the outer layers apart. It fuses the remaining elements in a frenzy of nuclear alchemy, creating the gold for your ring, the iodine for your blood, the uranium for your reactors. The star is ripped to shreds. What was once a silent, burning sphere is now a supernova, an explosion so bright it can outshine an entire galaxy of 100 billion stars. The father is dead. The iron catastrophe is complete. But the violence has just begun. The shockwave is now traveling outward, carrying with it the heavy elements, the seeds of future worlds, expanding at millions of miles per hour into the surrounding darkness. This expanding shell of gas glowing with the energy of the explosion, is no longer a star. It has become something else. It has become a nebula. The cycle is resetting. The debris from this catastrophe will drift for eons, cooling, mixing, and waiting for gravity to begin the work again. But as we watch the shockwave expand, tearing through the quiet neighborhood of the galaxy, we must remember everything we are, every atom in our bodies, was forged in this fraction of a second. We are the children of the catastrophe. We are the dust that survived the fire. And as the shockwave hits the surrounding clouds of hydrogen, it doesn't just destroy. It compresses. It creates new knots of density, new seeds. The death of this star is the trigger for the birth of the next. The violence is not senseless. It is necessary. It is the heartbeat of the cosmos, pulsing on a timescale we can barely comprehend. The iron that killed the star is now drifting free, ready to become the core of a new planet. A planet that might, one day, billions of years from now, have eyes to look up and wonder where it all came from. This is the violent beauty of the nebula. It is a graveyard, yes, but it is a graveyard where the tombstones are the cradles of the unborn. But there is a missing piece in this story of creation, a flaw in the narrative that astronomers struggled with for decades. We have seen how the star dies. We have seen how the iron core collapses, triggering the supernova that scatters the seeds of life. We know that the calcium in your bones and the iron in your blood were born in those final frantic moments of a massive star's life. But if you look at your hand right now, you might see something that the supernova could not create. You might be wearing a ring of gold, or perhaps platinum. These elements are heavy, far heavier than iron, and this presents a fundamental problem in our understanding of the cosmic machinery. You see, a standard supernova, for all its terrifying power, is not hot enough or violent enough to forge these precious metals in the abundance we see on Earth. The fusion inside a regular star stops at an iron. Fusing iron consumes energy rather than creating it. It is the ash that clogs the furnace. When the star explodes, it can create small amounts of heavier elements, but the math never quite added up. There simply wasn't enough energy in a standard explosion to account for the sheer amount of gold in the universe. For a long time, this was a dark mystery. Where did the treasures of the Earth come from? If the stars couldn't make them, and the supernovae couldn't forge them in sufficient quantities, then there had to be another process, something rarer, darker, and infinitely more violent, hiding in the deep silence of the cosmos. To find the origin of your jewelry, we must return to the graveyard. We must look at what is left behind after the supernova fades. When the shockwave has moved on and the nebula has begun to glow, there is often a corpse left in the center of the devastation. If the star was massive, but not quite massive enough to tear a hole in reality and become a black hole, it leaves behind a neutron star. This is an object that defies all human intuition. Imagine a sphere the size of a modern city, perhaps 12 miles across, but containing the entire mass of our sun. This is not rock. This is not gas. This is matter crushed beyond the limits of atomic structure. The gravity is so intense that the electrons have been smashed into the protons, merging to become neutrons, resulting in a density that is terrifying to contemplate. A single teaspoon of this material would weigh 1 billion tons. If you were to drop a marshmallow onto the surface of a neutron star, it would strike with the force of a nuclear warhead. This is the most hostile environment in the universe, a place where the laws of physics are pushed to their breaking point. Usually these stellar corpses sit alone in the dark, spinning rapidly, beaming radiation across the galaxy like cosmic lighthouses. But sometimes In the crowded, chaotic clusters of a nebula, two of these monsters are locked in a dance. They are a binary pair, born together, living together, and dying together. Now, as neutron stars, they are trapped in a decaying orbit, circling each other in the cold vacuum. This is not a peaceful waltz. As they spiral inward, their immense gravity churns the fabric of space-time itself. They generate gravitational waves, invisible ripples that stretch and squeeze the universe as they propagate outward. For millions of years, they draw closer, their speed increasing, their orbital period shortening. They are stealing energy from one another, inching toward an inevitable catastrophe. The tension builds over eons, a silent countdown ticking away in the darkness. And then, it happens. In a fraction of a second, the two city-sized atomic nuclei slam into each other. This event is known as a kilonova. It is a collision of such unimaginable violence that it makes a standard supernova look like a sparkler. The energy released in this single crash can outshine an entire galaxy. But it is not just the light that matters. It is the alchemy. This is the moment the universe becomes a factory. In the intense heat and pressure of the merger, a specific type of nuclear magic takes place, something physicists call the R process, or rapid neutron capture. It is a chaotic, messy kitchen. The environment is so flooded with neutrons that atomic nuclei are bombarded faster than they can decay. They are force-fed neutrons, bloating up into massive, unstable monsters, climbing the periodic table in a frenzy of creation. In the blink of an eye, lighter elements are smashed together to form the heavyweights: iodine, xenon, uranium, platinum, and gold. For decades, this was just a theory. The math worked, but we had never seen it happen. We had no proof that these cosmic recycling plants actually existed. That changed on August 17, 2017, with the event known as GW170817. Detectors on Earth caught the ripple in space-time, the gravitational wave passing through our planet. Almost simultaneously, telescopes swiveled to spot the flash of light in a distant galaxy. We saw it. We saw the two neutron stars collide. And in the spectrum of that light, we saw the unmistakable signature of heavy elements being born. The data from that single event was staggering. In that one collision, those two dead stars forged an amount of pure gold, estimated to be between 3 and 13 times the mass of the entire Earth. Just pause and visualize that. 13 solid planets made of gold, blasted out into the void in a single second. It completely revolutionized our understanding. We realized that the universe is a violent place, yes, but that violence is the only method of manufacturing the precious materials we value so highly. Before we follow that gold from the depths of space to the surface of our planet, I want you to stop and think about the object that might be resting on your finger or sitting in your jewelry box right now. We often look at gold as a symbol of status, of wealth, or of eternal love, because it does not rust or tarnish. It is unchanging. But knowing what you know now, that it was born from the death spiral of two crushed stellar cores, does that change how you see it? Does the violence of its origin make it less romantic? Or does the fact that it survived a cataclysm to get to you make it more sacred? I'd love to hear your perspective on this. Go to the comments below and tell me, if you could witness the terrifying event that forged your wedding ring, would you still view it as a simple luxury or as a relic of cosmic survival? The story of that gold atom did not end with the collision. In fact, that was only the beginning of its odyssey. After the kilonova, the newly forged gold was not a solid nugget. It was a cloud of superheated plasma, blasted outward at a significant fraction of the speed of light. It became part of the debris field, expanding into the interstellar medium. It mixed with the hydrogen and helium that had been drifting there since the Big Bang. It mingled with the iron and silicon left over from other supernovae. It became dust. For millions of years, this dust drifted through the galaxy. It was cold, dark, and silent. The violence of its birth was a distant memory. But gravity never sleeps. Slowly, inevitably, this dust began to clump together. It found a new stellar nursery, a vast nebula, where a new generation of stars was waking up. This particular cloud of dust and gas began to collapse. In the center, a yellow star ignited, our sun. But the gold atom remained in the disk of debris, swirling around the newborn star. It collided with grains of ice and rock. It was baked by the radiation of the young sun and frozen by the vacuum of space. As the planets began to form, clumping together like dirty snowballs, the gold was buried. It was trapped inside the molten heart of a protoplanet that would eventually become Earth. It sank deep into the core, pulled down by gravity, hidden beneath thousands of miles of rock. There, it waited for billions of years. It waited while the surface cooled. It waited while the oceans formed. It waited while the first single-celled life flickered into existence in the primordial soup. It wasn't until the Earth itself grew violent that the gold returned to the light. Volcanic eruptions and shifting tectonic plates dragged the metal up from the depths, depositing it in veins of quartz near the surface. There it sat, patient and eternal, until a miner's pick struck the rock and the cycle of discovery began. This is the true alchemy of collision. The universe is a closed ecosystem. Nothing is wasted. Nothing is ever truly lost. It is a relentless recycling plant, where destruction is merely a prerequisite for creation. The stars must die so that the elements can be born. The neutron stars must collide so that the heavy metals can exist. The nebula must collapse so that the planets can form. When you look at a nebula, you are not just looking at a pretty picture of gas and dust. You are looking at the warehouse of parts for the next solar system. You are looking at the laboratory where the ingredients for life and civilization are being mixed. The chaotic swirls of the Orion Nebula or the Carina Nebula are not static paintings. They are snapshots of a violent, churning process that has been operating for 13 billion years. Consider the pillars of creation. We see them as majestic towers, enduring and strong. But the research from the James Webb Space Telescope reveals a different truth. They are eroding. The massive, bright stars nearby are blasting them with ultraviolet radiation, stripping away the gas, carving down the mountains. They are evaporating before our eyes. The stars hiding inside those pillars are in a desperate race against time. They must gather enough mass to ignite and stabilize their own solar systems before their protective nursery is blown away completely. If they fail, they will be stillborn, failed stars drifting in the void. If they succeed, they become the new suns. This constant tension between construction and destruction is the engine of the cosmos. It is a brutal efficiency. The universe does not care about the beauty of the nebula. It cares about the transmutation of matter. It cares about taking the simple hydrogen of the beginning and forging it into the complex tapestry of elements we see today. And you are the beneficiary of this violence. The iodine in your thyroid that regulates your metabolism, forged in a kilonova. The uranium that heats the Earth's core, driving the plate tectonics that keep our planet habitable, forged in a kilonova. The platinum in the catalytic converter of your car, forged in a kilonova. We are connected to these distant, terrifying events in the most intimate way possible. We are not just observers of the universe. We are composed of its history. Every heavy atom in your body has traveled through the hellfire of a stellar death to be part of you. You are a collection of cosmic debris, assembled by gravity and animated by life. The nebula is the stage where this drama plays out. It is the beginning and the end. It is the Alpha and the Omega. As we gaze into these clouds, we are looking into the mirror of our own origins. We see the violence that made us and the beauty that resulted from it. But the cycle is not over. Our own sun is a middle-aged star. It has burned for 5 billion years, and it has 5 billion more to go. But one day, it too will run out of fuel. It will not explode as a supernova. It is too small for that. Instead, it will swell into a red giant, consuming Mercury and Venus, and perhaps Earth. It will shed its outer layers, puffing them gently out into the solar system. Our solar system, the place we call home, will eventually become a nebula. Future astronomers, looking from a distant galaxy, will see a faint glowing ring of gas where we once lived. They will analyze its light and see the signature of carbon, nitrogen, and oxygen. They will see the dust of a dead world. And in that dust, floating in the expanding shell of gas, will be the atoms of gold that once made up your ring. They will be returned to the void, ready to be swept up into the next cloud, to be part of the next star, to be worn by the next living thing that dares to look up and wonder. This is the promise of the nebula. It is a promise that life is resilient, that matter is eternal, and that out of the greatest violence comes the greatest beauty. The alchemy of collision is not just about nuclear physics. It is about the continuity of existence. It teaches us that we are small, fleeting sparks in a vast, dark night. But we are also rare and precious. We are the thinking, feeling dust of the cosmos, briefly awake to appreciate the majesty of the process that made us. So the next time you see an image of a nebula, do not just see a cloud. See the violence, see the shock waves, see the collisions, hear the silent scream of the tearing atoms. And then, look at your hand, feel the weight of the gold, and realize that you are touching the ghost of a star. You are wearing the wreckage of a collision that shook the universe. You are the evidence that in the cold, dark expanse of space, destruction is never the end. It is simply the way the universe prepares for the next beginning. The graveyard is not empty. It is full of seeds. And as we drift through these cosmic clouds, we realize that we are not just traveling through space. We are traveling through time, witnessing the eternal, violent, beautiful cycle of the stellar forge. And then, there is silence. It is a silence deeper than any ocean and older than any mountain. After the screaming fury of the supernova, after the tearing of the fabric of space, and after the blinding flash that outshines an entire galaxy, the noise fades. The shock waves ripple outward, dissipating into the vast, indifferent dark. The fire cools, the light dims, and what is left is not emptiness, but a graveyard filled with the most precious debris in existence. We have spent this journey witnessing the violence of the stellar nurseries and the catastrophic detonations of the cosmic graveyards. We have seen stars eat each other and nurseries evaporated by the glare of their own children. But now, we must turn our gaze away from the telescope and look at something far closer, yet infinitely more mysterious. Look at your hand. Turn it over. Watch the way the light catches the skin, the veins, the subtle tremors of life. You are looking at a ruin. You are looking at the wreckage of a collision that shook the universe long before the Earth was born. We often speak of the cosmos as something out there, a distant theater of lights and shapes that we observe from the safety of our small blue box. But that distinction is a lie. The violence we have described, the crushing gravity, The searing heat, the atomic annihilation, is not just a story about the sky. It is the biography of your body. Consider the blood pulsing through the veins in your wrist. It is red because of hemoglobin, a molecule built around a core of iron. That iron is not just a metal. It is a fossil of a star's final desperate day. Deep in the research of cosmic history, we find the iron catastrophe. For millions of years, a massive star lived a stable life, burning hydrogen, then helium, then carbon. But in its final 24 hours, a mere blink in cosmic time, it began to fuse silicon into iron. This was the death knell. Fusing iron does not create energy, it absorbs it. In that last day, the star committed suicide, and the resulting collapse generated the iron that now anchors your blood. Every time your heart beats, it is pumping the debris of a star that died so that you could live. Now, look at the ring on your finger or the gold chain around your neck. The history of that gold is even more violent. Standard supernovae, for all their power, are not hot enough to forge the heavy, precious metals we covet. For decades, this was a mystery. Where did the gold come from? The answer, confirmed only recently by the detection of gravitational waves, is the kilonova. This is the collision of two neutron stars, city-sized spheres, of pure nuclear density slamming into each other at a fraction of the speed of light. The resulting explosion is so intense that it forces extra neutrons into atomic nuclei, transmuting matter into gold, platinum, and uranium. The gold in your jewelry was not mined from the Earth. It was blasted across the galaxy in a cataclysm that would have sterilized anything within 100 light years. You are wearing the shrapnel of a galactic war zone. We are the calm after these storms. We are the ash that settled when the fires went out. But the journey from the graveyard to the nursery is not a straight line. It is a drift through the terrifying void. When we see images of nebulae, those towering pillars of gas and dust, we imagine them to be thick, heavy clouds, like a foggy morning on Earth. But this is an illusion of scale. In reality, a nebula is a better vacuum than any we can create in our finest laboratories. On Earth, the air you breathe has billions of particles in every cubic centimeter. In a nebula, there might be only 10,000 particles in that same space. If you were to scoop up a chunk of a nebula the size of the Earth, it would weigh only a few kilograms. These clouds are ghosts, barely there, held together only by the tenuous grip of gravity and the pressure of light. And yet, in this near vacuum, something miraculous happened. The dust did not just drift forever. It began to clump, driven by shock waves, perhaps from a nearby supernova, maybe the very one that created our iron. The great solar nebula began to spin. It flattened into a disk. The center ignited to become our sun, a second-generation star, burning the recycled fuel of its ancestors. But in the cooler outer rings, the dust began to stick. Grain by grain, pebble by pebble, the debris of the cosmic graveyard coalesced. The gold, the iron, the carbon, the oxygen, they found each other in the dark. This is the moment where physics became chemistry, and chemistry became biology. We have spoken of the great filter, the idea that nebulae are dangerous places where gamma-ray bursts and stellar winds sterilize young planets. And this is true. The pillars of creation are eroding mountains, evaporating under the glare of O-type stars. Any solar system forming there is in a race against time to gather mass before the nursery is blown away. We are the lucky ones. We are the survivors of the nursery. Our ancestral cloud was shielded just enough, or dense enough, to survive the radiation bombardment. In that protected pocket of the galaxy, the dust did something unprecedented. It learned to think. This is the aha moment of our journey. The synthesis of all the violence and beauty we have explored. We are not separate from the nebula. We are the nebula, condensed. We are the chaotic, swirling gas clouds that have cooled down, solidified, and developed a nervous system. When you look up at the Orion Nebula, you are not looking at an alien object. You are looking at your own baby pictures. You are seeing the raw materials of your own consciousness spread out across light years, waiting to be gathered. It is a humbling realization. We tend to see ourselves as the center of the story, the protagonists of the universe. But in the grand scale of the stellar life cycle, we are a byproduct. We are the slag, the leftover heavy elements that the stars could not use, clumped together on a rock, orbiting a yellow dwarf. And yet, this byproduct is the only thing in the universe that can appreciate the process. Without us, without the ash that learned to think, the nebulae would just be silent explosions in the dark. There would be no one to marvel at the colors, no one to calculate the age of the stars, no one to feel the awe of the infinite. We are the universe's way of knowing itself. But the cycle is not over. We are not the final destination of this matter. We are simply a temporary vessel. Just as we were born from the death of stars, our own star will eventually die. The sun, our giver of life, is burning through its fuel, ticking down the clock, just like the iron-fusing giants of the past, though at a much slower pace. In about 5 billion years, it will exhaust its hydrogen. It will swell into a red giant, consuming Mercury and Venus, and likely scorching the Earth into a lifeless cinder. And then, it will shed its outer layers. Recent models by astrophysicists like Albert Zylstra suggest that our Sun is right on the edge of the mass limit required to create a visible glowing nebula. It will likely produce a planetary nebula, a misleading name, as it has nothing to do with planets. It will be a shell of glowing ionized gas, expanding outward into the galaxy. The carbon in our bodies, the oxygen in our lungs, the iron in our blood, and the gold in our rings, all of it will be liberated. We will be returned to the void. Imagine that future. An alien astronomer, billions of years from now, looking through a telescope at the place where our solar system used to be. They will not see Earth. They will not see the pyramids, or the skyscrapers, or the internet. They will see a faint, glowing ring of gas, fading slowly into the night, a new nebula. And in that nebula, the dust will begin to cool. The atoms will drift. Gravity will catch hold of them once again. A new shockwave will pass through, and the cycles will begin anew. New stars will ignite. New planets will form. And perhaps, on one of those worlds, a new consciousness will awaken, look up at the sky, and wonder where it came from. They will not know that their atoms once belonged to a species that laughed and cried, and looked at the stars with wonder. They will simply feel the pull of the cosmos, the ancient memory of the fire written in their cells. This is the violent beauty of the nebula. It is not a painting, it is a machine. It is a recycling center on a galactic scale, ensuring that nothing is ever truly lost. We are transient, yes. Our lives are flickers in the dark. But the matter that makes us is eternal. We have been stars before, and we will be stars again. So, we return to the silence. The silence of the void is not empty. It is pregnant with potential. It is waiting for the next explosion, the next collapse, the next birth. We are the travelers between the stars, the sentient pause in the eternal conversation between gravity and fusion. We are the dust we are. This perspective changes everything. It strips away the trivial worries of our daily lives and replaces them with a profound sense of connection. You are not small. You are dense. You are a concentrated masterpiece of cosmic engineering, forged in the most violent fires imaginable, drifting through a universe that is mostly empty space. You are rare. You are the exception. And this brings us to the edge of our understanding. We have traced the physics, the chemistry, and the history. But there is one question that science cannot fully answer, a question that lingers in the silence between the heartbeats of a dying star. If the universe is a cycle of death and rebirth, and if we are the consciousness of that universe, what is our responsibility to it? Are we simply observers, destined to watch the show and then dissolve back into the gas clouds? Or does the fact that we can understand the process give us a role to play in it? If we are the only part of the nebula that can think, that can dream, that can love, does that make us the purpose of the explosion? The nebula does not care if we exist. The supernova does not mourn the destruction of the solar systems it vaporizes. The universe is violent, chaotic, and indifferent, and yet here we are. We care, we mourn, we create. In the cold, mechanical cycle of stellar evolution, we are the spark of warmth that defies the entropy. We are the evidence that the universe is not just a graveyard, but a garden. As you go about your life, remember the heat of the collision that forged your ring. Remember the collapse that colored your blood. And remember that you are not just in the universe. You are the universe, briefly awake, staring back at itself. This journey through the stellar nurseries and cosmic graveyards has shown us the machinery of creation. It has revealed that beauty and terror are two sides of the same coin, and that life is the resilient, stubborn residue of destruction. We have looked into the face of the Orion trap and seen our own reflection. We have walked among the pillars of destruction and found our origins. But the story is not over. The cosmos is vast, and there are mysteries we have yet to unravel. There are forces in the dark that we are only just beginning to see. I want to leave you with this thought. If every atom in your body has traveled through the hell of a supernova to get here, and if you're the result of billions of years of cosmic survival, then what are you going to do with this time? You are the calm after the storm. You are the legacy of the stars. Do not waste the stardust. What do you think is the most terrifying part of this cycle? Is it the violence of the birth, the inevitability of the death, or the silence that follows? Or do you find comfort in knowing that you are part of something so much larger than yourself? I want to hear your story in the comments below. Tell me how this perspective changes the way you look at the night sky. And if you want to continue this journey with us, if you want to explore the black holes, the galaxies, and the edges of time itself, then make sure to subscribe and ring that bell. We are building a community of curious minds, a gathering of stardust, looking for answers in the dark. Join us. Let's explore this beautiful, violent universe together. Until next time, keep looking up. The stars are watching.